Okay. So then we have our saturation line, 100% relative humidity. That's as much moisture as that temperature can hold. And so, same thing here. I look and say, this one right here, this one holds more, and this one holds more. They go up as it moves. And the same thing as I look at temperature, if that's the 100% line, 55 degrees, 60 degrees, 65 degrees, 70 degrees. Every temperature is a bigger container that can hold more vapor, hold more moisture as we go up, right? So if I turn on my thermal hygrometer and it says, okay, it's 70 degrees and 40% relative humidity, and I want to know what the grains per pound are in that air, I'm going to say, well, the first thing I know is 70 degrees. There's my 70-degree line right there. So I'm going to be on that line. It's 40% relative humidity. So here is my intersection. If this is a map of the air, you are here. If it's 70 degrees and 40%, then that's what the air is on the psychrometric chart. That's where I'm at. And it wants to find the GPP, or grains per pound. And so I'd come across over here, because that's where we keep GPP. And I would say that's right around 44 grains, between 40 and 50, 44 grains per pound. All right. Let me just ask you this question. What if we took it all the way? This is 40% and this is 100% right here. That's our saturation line. If I take 70 all the way up to the top and come across here to the grains, it's 110 grains. Okay. So what that's telling me is 70-degree air, the most vapor it can ever suspend is 110 grains. That's 100%. That's saturated. That energy level, you look at all the different weightlifters, that 70 degrees can only hold up 110 grains of water vapor. Okay. So it can hold. That's a little more than that. So that's 136 grains right there. But if that was 110 grains of water, that's the most that 70 degrees can ever suspend. That's the only amount of energy it has. It can hold it. Somebody help me out. If 70-degree air at 100% can hold 110 grains, what's 110 times 40%? So 110 times 0.4 or times 40%.
44.
44? Okay. Oh, wait a second. I see what's going on here. So what we're saying is 70 degrees at 100% can hold 110. If it's currently holding 44, what we're saying is 70-degree air that's holding 44 grains is at 40% of its capacity, or has a relative humidity of 40%. The other way I could say that is, if it's 70 degrees and it's 40% of its capacity, it's holding 44 grains. So every temperature can hold so much water vapor. Right now, how much is it holding? Right? Just look at one thing here real quick. Sorry, I made a couple of adjustments. So I want to make sure I'm not gonna. Okay. So, and this just goes by what I was talking about a moment ago, is 70 degrees at 100% relative humidity is 110 grains. That's as much as it can hold. And every temperature has that. So if I look at these these 5 containers right here, what do they have in common? They're all 50% full. What's different? Well, they're different size containers. So if each container, can hold more than the last one, then 50% of more is more, right? And so the line has to go up as it increases. So if I'm trying to chart 50% on all these different containers, it's going to be a line that goes up because each container is a little bit bigger as we look at that. Well, if we put this on the psychrometric chart, that's exactly what's happening, is each temperature can hold more moisture. And so the percentage line has to go up as the temperature gets higher because it can hold more. And so, for example, I like 70 degrees. We'll play with that again. 70 degrees at 50% coming across here is between 50 and 60 or 55 grains. Because 70 degrees at saturation, the most it can hold is 110 grains. If it can hold 110 and it's holding 55, it's at 50%. If it can hold 110 and it's at 50%, it's holding 55. Okay. So another just example I'm going to use on this, I have in this bag right here, dun, 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 10 juggling balls. And just because I'm curious, I want you to put real quick in the chat box your guess on how many of these 10 juggling balls you think I can juggle. Do I have some hidden talent that we're about to find out about? So go ahead, chat box. How many is 10 juggling balls? So 1, 2, 3. 1, I got faith. 7. All right, nice. 1, 1. Ouch. 5, 5. 0. Well, the rest of you have a chance to pass the exam, so that's good. 4. All right, 0, 3. All right, let me ask you this question. If I take one juggling ball and I do this, is that considered juggling? Because if it is, the answer would be 1. If it's not, the answer is 0. I can't juggle at all. So here's the point I'm trying to make, though. Let's say that I could juggle all 10 juggling balls. That was my capacity. I practiced a lot. I did 10 juggling balls. Does that mean that only 10 juggling balls will fit in the air? No, thousands will fit in the air. It just means that I only have the ability or capacity to keep 10 up in the air at any given time. So if I can do 10 and I'm doing 3, you ready for this? It's actually a new record. I've never done that well before. If I'm doing 3 juggling balls and I can do 10, I'm at 30% of my capacity. Somebody throws me another one, 4, 40%, another one, 5, 50%, another one, 6, 60%. The more juggling balls you throw me, the more energy it takes to keep them up in the air. Another 7, I'm at 70% of my capacity. 8, 80%, another one, 9, another one, 10. I'm at 100% of my capacity. I can do 10, I'm doing 10, that's it. If someone throws me another juggling ball, I have 2 options. I ignore it and let it fall back down to the ground, or I throw one of these out and grab that one and bring it in. But I have to get rid of one to take another one. That's as much as I can possibly do. And if I'm doing 3 balls out of 10, I'm at 30%. So a percentage says how much can you do and what's your percentage. If I went to, let's say we went to a juggling convention and everybody at the convention had a t-shirt on with how many juggling balls they can do. So I don't know, I would have 10 if that's what I could do. I got 10, someone's got 3, a 4, a 5, someone's got 12. I think the world record's like 16 or something. So I can look and say, okay, those 2 people are both doing 3 juggling balls. Their t-shirt says 3, they're at capacity. Their t-shirt says 6, they're only at 50% of capacity. I can see what they can do and I can count how many they're doing. Well, that's what's happening with our relative humidity is every temperature is a vapor juggler. And the higher the temperature, the better the juggler. 50 degrees right here. In fact, let me just jump these off here real fast. So 50 degrees right here as a vapor juggler can do about 54 GPP. He can keep 50. That's it. That's as high as he can go. 60 degrees as a vapor juggler can do about 80 grains. 65 degrees, about 94 grains. 66 degrees, right? Every temperature can do a little bit more vapor. So when you look at the temperature down here, I used to look at temperature and go, oh, that's how warm the air is. Now I look at temperature and I say, oh, as a vapor juggler, that tells me how many grains they can do over here. The temperature is the indicator of how much water vapor, how good of a juggler that temperature is. And every degree higher is a little bit better at keeping water vapor in the air. Okay. And so we're saying how much can you do and how much are you currently doing and what's the percentage. So when we look at using this example, and you know I'm serious about this because I'm talking about relative humidity and I'm going right for the juggler. Oh my gosh, I'm sorry. I don't want to say stupid things. I just can't help myself sometimes. So when I look at these, I say, what is similar? What's the same on these? Well, they're all at 50%. That's exactly the same. What's different? Well, since their capacity is different, what they're actually doing is different. They're all at 50%, but 50% for him is 2. She can do 6, 50% is 3. He can do 8, 50% is 4. So they have the same percentage. This is why I cannot compare percentages. Because unless it's the exact same total, percentage will be totally different. I'm never comparing relative humidity to relative humidity. I'm only using it to find out where I am on the chart, okay? So let's look at this kind of psychrometrically. What's the same in all 3 of these air masses? 40 degrees at 50%, 60 degrees at 50%, 80 degrees at 50%. Well, just like we have better jugglers, the warmer the temperature, the greater capacity. So if this air right here was at 40 degrees and 50% relative humidity, it would have 18 grains of moisture floating around in it. But if it was 60 degrees and 50%, it would have 39 grains of moisture. And 80 degrees can hold a lot more, better juggler. So if it's at 50%, just like this is a better juggler, it would have 77 grains floating through it. Let's take a look at this on the psychrometric chart. I have these 3 air masses. What is the same? They're all at 50%. They're all going to be represented on that 50% line. What's different? The capacity. 40 degrees is right here. That's the 40-degree line. And 50% is right there, halfway up. 60 degrees is right here. That's the 60-degree line. And that's halfway up. Goes up to get there. 80 degrees is right here. And that's the 50% line. That's halfway up for 80 degrees. So now the difference would be 40 degrees. If I go across to the right, that's where the GPP is. Let's go see what it is. It's going to be right there at about 18 grains per pound, right below 20, 18 grains per pound. 60 degrees at 50% is right there just below the 40 at about 39 grains. And 80 degrees at 50% right here comes across, and that's going to be just below the 80 at about 77 grains. So every temperature is an indicator of how much moisture that air can hold. Relative humidity says, compared to that, how much vapor do you have in the air compared to what you're capable of doing? So 77 GPP versus 39 versus 18. Really slow right there. Okay, something's up. I was playing with that slide. I got to fix that. 296. I will get it. Okay. But that's where line up. So now another example with our jugglers. What's the same? They are all doing 4 juggling balls. They all have the same amount of juggling balls in the air. What's different? Well, for him, that represents 100% of what he can do. For her, it's 66%, and for him, it's 50%. Okay, let's now look at the air. If this air right here was at 40 degrees and it had 36 grains of moisture, that's its capacity. It's 100% full, just like this juggler. But if this air was 60 degrees, a better juggler, 60 degrees, can suspend or hold 78 grains. It's only holding 36. That represents 47% relative to what it can do. And if this air was 80 degrees, which has the capacity of 154 grains, only holding 36 grains, that would only represent 24% of its capacity or relative humidity. Let's look at that on the psychrometric chart. So I say, okay, what's the same? 36 grains. This is very similar to me pouring the water back and forth at the very beginning. All 3 of these air masses, these samples have 36 grains. They're going to be on this line. What's different? Well, the first one's at 40 degrees, and so that's right there at 100%. That's as much as it can hold. 60 degrees is right here, and it matches up right there. Well, this is 50%, and this is 40%. So here's the 50% line and the 40% line, and it's right here, I would say, at about 47%, a little bit below 50, right there. And then 80 degrees is right here, and 24%, or I'm sorry, that's right, 80 degrees with 36 grains in it would be right here. And so we say again, let me get that out of there. This is 30% right here, and this is 20% right here. And I say how far below and how far above, and that's a little less than halfway, or 24% between the two. Do one more. What's the same? They're all at capacity. They're all doing as much as they can. What's different? Well, for him, capacity is 4. For her, it's 6. For him, it's 8. All right. What's the same on these? They're all at 100% capacity. What's different? 40-degree air at 100% relative humidity can only hold 36 grains. That's it. Whereas 60-degree air can hold 78 grains, and 80-degree air can hold 154. On the psychrometric chart, what's the same? They're all at saturation. All these samples are completely full. What's different? What full is for each one of them. 40 degrees at complete saturation is, as a juggler, as a vapor juggler, 40 degrees can do 36 grains. 60 degrees can do 78 grains. And 80 degrees can do about 154 grains right there. So that's what we're saying with temperature and relative humidity is in this section of air, which represents all the other sections of air. You can actually go through, you can look at the grains on your thermohygrometer, figure up the cubic footage of the air, and find out how much exact moisture is floating through your space. It's not that tough to do if you want to do it. But we're saying in this section of air, what's the temperature? The temperature says what percentage, or temperature tells me how much moisture it can hold. If this was 70 degrees, it could hold 110 grains. And then the relative humidity says what percentage full is that, and I back it out. If this is 70 degrees and it can hold 110 grains, and my hygrometer says it's 50% relative humidity, then I know, well, if it can hold 110 grains, it's at 50% of that, it's currently holding 55 grains. If it's 40%, it's holding 44 grains, like we did a minute ago. We're going to do another exercise on that. So that's what we're talking about with the different air masses going through. Question. Oh, sorry. How did I get 18 GPP in the first one? To jump back a ways and see. Just what this. So I think what you're talking about was this one here. And I got 18 GPP by saying, here's 40 degrees. It's at 50% relative humidity. And so this right here is the intersection. If I come straight across, it's at 18 grains per pound. Let me know if that answered your question or not. There's no mathematical equation to see the GPP using RH and temperature to look at the chart. No, there is a mathematical equation, actually. And so when you look at this, it's just, so there's some formulas, like if you're converting between Fahrenheit and Celsius, it's like, okay, I take the degrees Celsius, divide by 6, add my age. I can't remember what it is, but there's a really simple formula that says if I do this, this, and this, it converts it from Fahrenheit to Celsius or vice versa. Psychrometry, there is a formula, but it's very, very detailed. It's not something you can remember and do quickly on a calculator. No. So, all right, and let me find. We do have, just if you want to play around with it, I'll put this in the chat box here. And this is just it's actually, I like this because there's different apps you can get that I like. This is actually, it's freescicalc.com, and it's web-based. So you can do it on your computer, on your phone, or whatever. And so if you're just looking for quick calculations on the psychrometry, it's right there, and you can use that. So, all right. Gonna get cranking. We got a lot to get through before this day is over. So, and then again, if you have any struggles, please ask. I will be here after class. I'll have my email. I will be here tomorrow morning. Please don't be frustrated. I hope you're all getting it. But if someone's not, please don't be just going, oh my gosh, this is crazy. I promise if you'll give me a chance, I'll figure out what I missed and I'll get you up to speed on it. So, all right. Come on, there we go. That's a lot of clicking to get out of there. So just one more thing real quick on the jugglers, almost our last one of them. If you look at these two right here and you say, okay, they're both at 50%, but since they have a different capacity, 50% is also going to be different. For the guy on the left, 50% is 2. For the guy on the right, 50% is 4. The guy on the left is doing 2 juggling balls. He's at 50%. If he throws those juggling balls to someone that's a better juggler, it goes from 25% to 50 or 50% to 25%. For a better juggler, those 2 balls are a smaller percentage of what he's capable of doing. Well, the same thing, if I have so many grains of moisture, I shouldn't say my grains. You're like, yeah, we all have a migraine, you idiot. The grains, if there's so many grains of moisture floating through the air, and I go turn the temperature up a ways, it doesn't change the amount of moisture in the air. If I turn it up enough, I guess eventually it could warm up the materials and cause more evaporation. Or if I turn it down enough, eventually it could hit dew point. But initially, just by turning up the temperature, what I've done is pour the water into a bigger container. I have the same amount of grains floating through the air in a greater capacity, so the relative humidity is going to go down. So just like this happened, if the water vapor gets thrown to a better juggler, a higher temperature, the percentage will go down, just like moving it cup to cup. So here's what I want you to get in your mind. Remember this. If temperature goes up or down, what doesn't change? GPP. It stays the same, right? Turn the temperature up and down doesn't change the amount of moisture in the air. It changes the holding capacity of the air, turns it into a better or a worse juggler. And so if temperature goes up and there's the same amount of GPP, relative humidity will go down. If temperature goes down, relative humidity always goes up. So I want you to visualize this teeter-totter or seesaw or whatever you want to call it. Whatever temperature does, relative humidity has to do the opposite. So
They try to get equilibrium as well.
not on this, no. No, this is just simply a matter of saying that if I change the size of the container, the percentage of moisture changes. It's at 25%. If I put it into a smaller container, it goes up to 50%. If I increase the temperature on the wall where there's so many grains in the air and I increase the holding capacity, then there's the same amount of moisture in a bigger container. So the percentage of what it's representing went down. That's all we're trying to say. It's a good question. Yeah, on this, we're just saying that there's just a direct relationship. Temperature, whatever temperature does, relative humidity does the opposite, just like pouring it back and forth between my jars right there.
Okay, so basically the containment are representing different rooms and different type of containments. So obviously the humidity in the air is going to be different, and we have to figure out what the humidity is before we can move forward, right? So
Yes.
that's the deal here. Okay.
Yeah.
So the
Yeah. And
juggler
so
containment, so the jugglers represent different sizes of rooms, buildings,
capacity.
yes,
Yeah.
capacities.
So, and even not different rooms, but the same room. Because what we're saying is in this room right now, if it's, if this room right now is at 70 degrees, it can hold. Well, you know what? Let me do this because you brought me perfectly to my next example. So I'm going to do what we just did another way because I think it's exactly what you're saying. So nicely done. And then we'll go. And if you have a question afterwards. So I'm going to show the math behind this. You'll never have to do this, but I just want to show for some people it kind of helps gel it a little bit. So 70 degrees at 100% relative humidity, as we know, can hold 110 grains. 70 degrees, 100% relative humidity has 110 grains. That's as much as it can hold. And so if I say, okay, I have air that's 70 degrees, and we already saw this on the chart. I'll show you again. At 100%, it could hold 110. Right now, it's at 44. What's the relative humidity? Relative to how much it can hold, what does this represent? What percentage is that? So all I do, remember, I'm looking for a percentage. Little car goes into big garage. So this is how much the air is holding, divided into how much the air can hold, 40%. Because 44 is 40% of 110. It can hold this much, and it's currently holding this much. That would be 40% of what it can hold. Let's look at this on the psychrometric chart. 70 degrees at capacity, at saturation, it's not where it is, but if it was at saturation, that could hold 110 grains. But that's not where it is. Right now, it's actually holding 44 grains. That's where it's actually at. So it's not a capacity, it's down here. So this is not the intersection. This is the intersection. And that intersection is where? Right there at 40%. So if the air at 70 degrees can hold 110 grains and it currently has 44, it's at 40% of what it can hold. In other words, if the air is at 70 degrees, it's capable of holding literally that amount of water in vapor form. If it's at 44, if that's in there, then that would be 40% relative humidity. Okay, this is how much it can hold. And right now it's holding that much. It's at 40% of what it can hold, or relative to that, it's 40%. What if we change the temperature? So we have this air that's 70 degrees and 100%. It can hold 110 grains, and it's at 110 grains. It's full. So if I have this container right here, a 1 cup container with 1 cup of water is full. I can't put any more water in there. If I want to, what I'd have to do is put it into a bigger container. Well, now there's room for more water. Same amount of water in a bigger container. So I'm saying is my container is 70 degrees. It can, at 100%, it can hold 110 grains. And right now it's full. It's holding 110 grains. Can't hold any more. But if I increase the temperature, it has a greater holding capacity. So if I go from 70 degrees up to 80 degrees, I know that if temperature goes up, right now I'm at 100% relative humidity. If temperature goes up, my relative humidity is going to go down. So it'll be less than 100% because I put it into a bigger container. And so what we're going to do on this is say 70 degrees can hold 110 grains, and it's at 110 grains. I'm going to increase the temperature up here to 80 degrees. This is my new temperature line, which means this is my new intersection, which is right here at about 71% relative humidity. Here's how we got there. And again, you'll never have to do this. I'm just showing you what it is behind the scenes. 70 degrees at 100% can hold 110 grains, and it's at 110 grains. If I increase the temperature from 70 degrees up to 80 degrees, the new capacity is now 154. This has gone up to 154, but this has stayed the same. So where this was full, now I have 110 grains in air that can now hold 154. 110 divided by 154 is 71%. 110 grains is 100% of 110 grains, but it's only 71% of 54 grains. So by increasing the temperature of the air, where it can now hold more moisture, the relative humidity goes down. All right. How are we doing on GPP and relative humidity? Are we okay on that? If it's not making sense, you got to tell me. I'm seeing a couple of doughy eyes of people I'm a little concerned about. So if you'll stay after class, it won't take long. I'll figure out where I did miss. Because usually what happens is there's some place that I made a statement and somebody latches onto it and they're like, well, what about this? I don't see how it works. And when I can unwind that a little bit, they go, okay, Now I see where it is. So if you're struggling, I apologize for that. I think we're mostly getting there. So if
And
I
then
do,
yeah.
go ahead. Sorry, you're
No,
good.
no, I'm and then now you're pretty much so the drying equipment, that's when the drying equipment and your equipment comes into play here, right? So this
No,
is
not
no.
yet. You're getting ahead of me. You're right on the right track, but you're getting ahead of me.
Well, I'm saying in order to raise the temperature or lower the
Oh,
temperature, you
that's the thermostat on the wall.
copy that.
Yep,
Okay.
yep, yep, yep. Yeah, you're going
Okay.
the right way. Your head's going the right direction. Just jumping a little bit ahead of me there. So,
Okay. Okay.
will these questions be the same like the formula questions? Will be four answers different from each other? So on this stuff right here, just so you know, there's nothing like this on the exam. There is nothing nearly this easy on the exam. No, I'm totally kidding. So, what you'll want to do on the exam pretty much is on the cyclometric chart is be able to navigate it. If it's this GPP and it's this relative humidity, what's the temperature? Be able to say, if I know this and this, where does it put me? If I'm right here, what's the other information? So you want to just really kind of get around the chart by knowing a couple of different things on there. So yeah, they won't be. This is me teaching. The exam's not nearly this convoluted. So.
And then again, I have in my notes that you said above 66% of relative humidity can cause secondary damage. So
Potentially.
you would have to know the humidity percentage before even moving forward because you don't
Yeah,
know how much damage or
that's the
even
only time we ever are talking about relative humidity because otherwise, without knowing the temperature, it doesn't work. So yeah, if you're in a higher temperature, 66%, then they're saying there's enough moisture, you're getting close enough to the dew point where you could start to have some issues
copy
potentially.
that.
Yep.
Okay.
Yeah. Great comment. Sometimes it's hard to read the chart, the exact number. It is. It's a little tiny chart that's printed out. It's hard to read. And so I want to point out again that let's say an exam question made up, let's say it said, hey, on the exam question, it is 75 degrees and 40% relative humidity. What is the GPP? And you go, well, here's 75 degrees. Here's 40% relative humidity. The GPP is, and you say it's 51. And then you look over and the answer doesn't have a 51. It will not be 49, 50, 51, 52. If this was an exam question, the options would be like 26, 51, 73, 112. So you go, well, or let's say 52. Sorry. So you're going, okay, none of them are exact, but that's way closer than anything else. So because you're reading a chart, if what you think it is one or two off from one of the options on the exam, that's the one, right? They're not going to be close enough. We're not trying to fool you because it's a small 8.5 by 11 printout. Yeah, great point. Very important point. So, okay. So if I do get to 100% relative humidity, we call that dew point or the point of dew, the point of condensation. We have either dew point happens in one of two ways. I cool down the temperature enough that it can't hold any more moisture. And so if I keep putting in there, moisture comes out. Or I keep adding moisture to that air one way or another, where I get to the point where it's full. But most we say when we talk about cooling it down. So remember, going back to my example earlier, if I throw these magnets at each other with enough force, they're just going to bounce off. But when they start to slow down, they start to stick together again, and then they start to stick to stuff again. And so as we cool down the air, when we get to what we call dew point temperature, there's no longer enough energy to keep that moisture airborne. It's going to start to slow down, hit a surface, and stick to that surface through condensation, which is the opposite of evaporation. And that's we only want condensation to happen in one place, and that's our dehumidifier. It's obviously happening constantly back and forth. There's always going to be condensation and evaporation. I'll quit teaching on Thursday. I'll come back on Monday, and a bunch of the water's gone through evaporation. And it wasn't 212 degrees in here, I hope. So dew point temperature, a couple things about it. Dew point temperature, again, is the temperature of the point at which we get dew, where the air is saturated, can't hold any more. Doesn't mean any more won't fit in there, right? And 110 grains is not that much. A lot more would fit. It's just as much as that air can suspend. Surfaces below dew point are going to get condensation. If I had a piece of metal in my hand that was 32 degrees or colder and I put water on it, it would eventually turn into ice. If I have a piece of metal in my hand that's 212 degrees or hotter, it would burn the crud out of my hand. But if I put water in that, it would evaporate. Those two temperatures force a change in the phase of the water. Dew point temperature is not a number like 32 or 212 because it's based on 100% relative humidity, which is different for every one of us right now because we're all in different relative humidity. So it's a moving target, but it's based on what would put you, if I cool the temperature, if temperature goes down, relative humidity goes up. Well, if I keep putting the temperature down, it's going to keep going up until it hits 100% relative humidity, and that's dew point. So what temperature I have to cool it down to finally get those magnets to stick together and stick back to my flat bar is basically what you're saying. And this is the same as 100% relative humidity. This right here on the lower left is very common in Reno. That's called a rim joist, and you have to have insulation in your rim joist in Reno by code. And so they take insulation with paper backing on it, cut pieces, and shove it in there. And years later, when they get a home inspection, they pull it out. It's gotten condensation that couldn't dry fast enough through that paper back insulation. And it's just a big, moldy, rotten mess in there. Happens all the time. Condensation on a T-bar drop grid ceiling, condensation on the ceiling or on the glass. This is something we don't want to see. I've had it happen. It's a job with, got a lot of carpet, a lot of drywall that's wet. We do a really good extraction. We lift the carpet and pull the pad, and then we bring in a bunch of air movers and dehumidifiers to bring the moisture out of those materials. Well, there's already quite a bit going on in there. And it gets cold that night, below dew point. I come the next morning and there's water dripping down the windows and down the sliding glass door. So I get a towel and hope the homeowner doesn't notice while I'm wiping it off and feeling kind of stupid because I shouldn't have done that. And so I actually had one time where we showed up the next day and there's water dripping down the window, which is glass, no harm, no foul. But it went all the way down and hit the wood stained windowsills and split them out. And I had to buy new ones. And it came down the sliding glass door and hit the carpet. And it slightly stained it and slightly delaminated. Now I was able to get my installer over there and stretch it and make them happy, but I could have been buying all new carpet. And so I'll be right with you. Hold that thought for just a second. And so for me, if it's going to be cold that night and there's a lot of wet materials I'm trying to dry out, on day one, I might put little to no air movers in there. I might just bring in a lot of dehumidification. Let's get it under control. And the next day, when I've got everything under control, now I'll bring in my air movers and start to try and cause evaporation out of my materials. Carlos, go ahead.
Okay, so basically the lower the dew point, the more the condensation and the moisture. Oh, wait. Can you hear me?
Yeah.
Oh, okay.
So the higher as the dew
The
point goes
higher.
up, I get to 100% relative humidity as my dew point. So as dew point's going up, I'm getting closer to saturation.
Okay, I just got confused because
Yeah.
I don't know. I was reading the slide and then I was looking at the chart and I was like, wait, but the dew point shows higher and then the vapor shows higher as well. So I was just
Yeah.
confused.
The higher the dew point temperature, the more moisture that's in the air.
Cool. All right. Thank you
Yeah.
guys.
Yep. No, and we're going to go through this a little bit more. So there's two things happening with dew point. At or below dew point, condensation. I don't want that. Above dew point, evaporation. That's what I want. And that's what we're going to talk about here in just a moment. So this is the last slide with the jugglers on it. But you'll notice these two right here. The guy on the left can do 4 balls. The guy on the right can do 8 balls. If he's doing 4, he's at only 50% capacity. I could throw him another one and another one and another one and another one. And then he'd be full. He couldn't do any more. But if the guy on the right is doing 4 juggling balls at 50% capacity and throws them to the guy on the left, that guy on the left is now at capacity. He can do 4, he's doing 4. You throw him another one, he's going to drop one because he is at dew point.
Capacity.
He's at capacity.
And
Perfect. Thank you. Yeah, can't hold anymore. And so as temperature goes down, it goes to you're throwing the balls to a worse vapor juggler, worse vapor juggler, worse vapor juggler till they start to drop them. Every temperature going down, it can hold a little bit less moisture in the air. And at some point, it's going to get to the point where it can't hold anymore. Hold on just a second. I get these little thoughts running through my head. And if I write them down, I can move on. Otherwise, they'll keep bugging me back there. So again, dew point temperature says 70 degrees at 100% can hold 110 grains. If it has 110 grains, it's at 100%, it's at dew point. It can't hold any more than that. Again, not because the container's full in this situation, but just because that's as much as the air can hold. So my dew point temperature is found on the same moisture line. It's just a little bit farther to the right on this chart. Okay. And so the dew point or the point of condensation, 32 degrees, the point of freezing. Dew point temperature, the point of condensation. And so I'm going to use just as an example here, 55 degrees dew point. So I come over here to my dew point, and there's 55-degree dew point. And that line right there represents 55-degree dew point. And it also, you'll notice, also represents 64 GPP. That's the moisture line. Everything over here is a direct measurement of the moisture in the air. So if one goes up, the other one goes up and down. It's a different way to look at, this right here is 16 ounces and 2 cups, saying the exact same thing. These are all saying the same thing, just in a different way. They're all a direct measurement of the same thing that's on there. All right. So 55-degree dew point. Right now in the room that I'm in, I am at a dew point of, I'm actually at 32-degree dew point, right? I'd have to get all the way down to freezing to get moisture out of this air. So here is 30, 31, 32. So I'm about right there is my dew point temperature in the room right here at about 27 GPP. Yeah, 20. Yeah, right there. So, all right. So that's my example of 55-degree dew point. So if you're in a room with a 55-degree dew point, any surface in there, and I want you to realize that when we talk about dew point, that's a temperature we take in the air, but where does it show up? On surfaces. That's where we get condensation, right? When we show up at grandma's house and get a glass of ice water, she says, "Don't you put that on my coffee table without a coaster." She's not worried about the water leaking out of the glass. She knows how condensation and dew point works. And so if there's any surface, when we talk about dew point, we're talking about surface temperature and condensation. So if you have a dew point of 55 degrees and you go get a can of soda or soda pop or pop, wherever you are in the country, out of the fridge and put it on the counter, pretty soon you're going to notice water droplets forming on that because it would be below the dew point temperature of that air. And so the moisture is going to hit that. I'll talk about that here again in just a moment. Does that mean the colder the room, the surface, the easier it is to extract moisture and water from? No, it's a great question, but no, because if it's cold, that affects what's happening. I'm extracting liquid water. I'm not trying to get the moisture to go back in that way to extract it. I'm going to get the liquid out and then evaporate it. So that's an interesting thought. It's a good thought, but yeah, it wouldn't quite work that way. But it's a great thought. I love the way your mind's working there. So, okay. On the full chart, it's just right there. That is my 55-degree dew point right there. So when we're talking about dew point, what we're really looking at is saying, I'm trying to dry stuff out. And so I want to be not just above dew point, but as far above dew point as I can. If I'm not above dew point, that's why we're using infrared cameras and lasers to find out the surface temperature. If you had ice on your driveway and somebody knocks on your door and says, "Hey, I noticed your driveway's frozen up like everybody else in the neighborhood. We have a machine that will melt the ice off your driveway. If you're interested, it'll cost you $200. I'm like, well, that sounds interesting. What do you do? Well, we just heat it up and melt the ice. So how hot does your machine get? It gets up to 35 degrees. If you're trying to melt ice that freezes at 32 and they have a machine at 35 degrees, is that going to melt ice? Eventually,
No.
yeah, anything above 32 is going to melt it eventually, but it's going to take a long, long time. Somebody else says, "Oh, we have a similar machine, but ours gets up to 85 degrees. Well, that's who I'm going to hire, right? If I go to the refrigerator, the freezer, and I've got this big clump of gnarly ice, it's all, it's been old ice, it's all stuck together. I pull it out, I put it in the sink. If I run cold water on it, it'll melt. If I run hot water on it, it melts really fast. So the bigger the difference in temperature, the faster that change is going to take place.
Yeah.
So if I've got someone who could get that ice up, not 35 degrees, but 50 degrees, 60, 80, 90 degrees, it's going to melt a lot faster. Well, the same thing is happening when it comes to the bigger difference between the temperatures. If I take my dew point temperature and it says your dew point temperature is 50 degrees, and the surface temperature of my floor that I'm trying to dry, maybe there's a cold crawl space, and the surface temperature is 50, that's like trying to melt ice on a 32-degree plate. It's not going to happen. I can't evaporate from a surface that's at or below dew point. Matter of fact, moisture is probably going into that surface. That's at dew point or the point of dew, which means if it's at or below dew point, moisture is moving into that surface. But if I have, I'll be right there 1 second. But if I have a 50-degree dew point and my surface temperature is 80, now I'm going to have pretty good drying taking place. Somebody wanted me to come back to this real quick. So I want my materials not just, remember that, if at or below dew point, at or below 32, freezing, at or below dew point, condensation, above 30, 33 and above, melting, dew point and above, evaporation. The higher above 32, the faster the melting. The higher above dew point, the faster the evaporation. It's just working exactly the same way. And so, okay, on your direct message on losing internet, if you will just send that to LTR staff so that they know, and then I can on something like that where you can't control it. Afterwards, you want to let me know. You know what? My recording is goofing up today. I don't know if I'm going to have it or not because it's doing locally, but if so, I might be able to find what section you missed and help you out with that if you know what it was. So anyhow, that's what we're saying is the bigger the difference, the better it's going to be. So if I have a dew point of 50 degrees and I'm trying to dry this floor, I don't want it at 55 or 60 degrees. I want it at 80 degrees. I want as high above that as I can get. And something you're going to notice more and more of, it used to be that our clients or the insurance companies say, hey, when you're giving us our documentation, we want to know the relative humidity and the temperature, the GPP, and we want the moisture content of the materials. Now more and more of them are saying, we want to know the surface temperature of the materials you're trying to dry, because they're going to do a dew point analysis. They're going to say, you're charging me for 9 air movers and 2 dehumidifiers. You have a dew point of 50 degrees and your materials were 53 degrees. That equipment was doing no good. And you know what? They're right. We should have caught that, and we should warm those materials up, because all we're doing is making a truck payment, and that's not fair. We need to be controlling those environments. So again, not a wonderful